where we continue looking at what we have already started. Can you see my slide?
Yeah, your slide is visible, sir.
Uh, all right. So um, we were talking yesterday. I think we stopped out at um, so we stopped yesterday at talking about training or fine tuning a language model is very time
There is
consuming. Not only
Jana,
time
yeah.
consuming, but also, it required a lot of resources that we may not have. We may be using Colab. So there are a lot of ways you can fine tune a very large model, but you do not update the all parameters. Sometimes you can update the whole, only the last layers. So you are not updating everything. So that's what we're talking about, you know, about this. We are talking about the problem of fine tuning. For example, 7 billion model require 80 gigabyte of GPU memory. And a lot of people, they don't have this kind of GPU memory. So this is a huge problem, and we need a better way to actually um, fine tune a model, even though we don't have resources. And what we saw yesterday is that you didn't need to update all the parameters of the model. If a model has 7 billion parameters, um, we can update maybe only 1% of those parameters, and at the same time the model achieve a good performance, maybe not a good performance as fine tune the whole parameters, but it can achieve maybe, as we said, 95 or to 95% close to the full fine tuning. So this approach, where we fine tune some selected parameters in the original model, is what we call parameter efficient fine tuning. Um, One of my student, Sukaraj, is working also in on parameter efficient fine tuning of Whisper, which basically he was trying to see whether using parameter efficient fine tuning on Whisper can be a good performance for Hausa speech, text to speech, or speech to text, something like that. So this is a good approach one can explore if you want to work on that. Okay, so we said, okay, we talk about parameter efficient fine tuning. So there are a lot of approach for one to do parameter efficient fine tuning. One is additive method. So additive method is from the name additive, you add something in your original model, right? So this is what we talk about. And the second approach is selective method. Choose existing parameters to update. So this one is you just choose some parameters to update. This one, additive, you add some layers and you update all those layers. But this is selective method. You only select some parameters and update. And this is another approach. Reparameterization changes how parameters are updated during training. So this is you decide how parameters are updated. So these are different three approach. And the very first approach we saw is additive, which we have what we call adapters. You add some layers and you only update these layers. And it has been shown that this approach was really good. But adapters, where we add something, has now been superseded with much better approach. Especially currently now, people are working on this reparameterization methods such as LoRa and other stuff. So this is an example of that. And we have something also, prefix tuning, which basically we add, prefix something at the end of, for example, here you can see if this is fine tuning. All right, this is fine tuning, right? Yeah, this is fine tuning, but we have what we call prefix tuning. So what is prefix tuning? It's a parameter efficient fine tuning. You can see because it's an approach to fine tune the language model efficiently that prepend trainable prefix. So if this is your transformer, so you append, trainable. So these are the only thing you append that you train them. prefix vectors to the model input at each layer while keeping the original model weight frozen. So the model weight here, they are all frozen. So you only frozen them. But here at the end, you prepend with some, prefix vectors, and now you update only this, and it has been shown, for example, in this work, prefix tuning, by this guy. It really works and give a good, so you can see the idea is prepend learnable continuous vectors to every attention layer. So these vectors that you append, they are learnable, meaning that you can learn from them, you can update them. So if they are learnable, it means you can update the weight and they can learn. And these subtoken guide the model attention toward the text. So different prefix for different tasks. For example, here you have summarization, you have translation, you have table to text. So different tags, you need to append different trainable vectors to do that. So this is actually also, you can see additive method because you add something. So you can see where we call additive method, adapters, prefix. There is another one, prompt tuning. So, and this is a paper for the prefix tuning. And we also have another thing, is what we call prompt tuning. Uh, so what this means is that is we talk about prompt tuning, right? What this means is that um, you know uh, now, for example, with ChatGPT, you have seen that you can do a lot of stuff without any, training the model. For example, I can give ChatGPT something, and it may not give me something good, but I can give it prompt. Oh, this is how to do this. Keep changing the prompt. When you give it a better prompt, then it learns. So this is what we call prompt tuning. So you use this is not fine tuning the model, because in fine tuning we are training the model, we are changing the parameters weight, yeah. But in prompt tuning, you can see learn specific task, virtual task, no architectural change, no added latency, something like that. So the intuition is that large language model can detect and follow subtle tasks in small model need more guidance. So so for large language models, they just need some stuff. So these are all, a way one can do that. So that's what we call the idea of additive method, but we also have selective method. So what are these selective methods? So this selective, instead of adding modules, decide which existing ones are most important to update. So that's idea. So this, they are not adding anything, but instead for them to update the whole, weight of the model, no, they just update sample of them, because not all weight are equally important for a new task. Selective method identify and update only the most tax relevant subset. So these are some work, you can see them. We don't need to go into a lot of them, but these are some papers that show that selective method is good. You can see here we say selective methods are powerful researchable, but LoRa is more commonly used in practice due to its simplicity and hanging face support. So now these are selective method. As you can see here, all of these are selective method. We have selective method, bitfish. All these are, actually from the literature, they are called selective method. But now people are using these ones to do parameter efficient fine tuning. But it's good for us to understand, what is parameter efficient fine tuning? What are the approaches people do? Which parameter efficient fine tuning? We have now understand that people do what we call additive method, where they add something. But even before LoRa, this additive method using what we call adapters, they are really good. Now another approach which is called selective method. Now we have something called LoRa and something like that. So this is what this guy is saying. Selective method are powerful, but LoRa is more commonly now used. Yeah. So this is what we have seen. Now we are now in a reparameterization method. What did that? So the reparameterization method, you can see them here include LoRa, all these LoRa, something like that. LoRa, QLoRa, and their variant. So what does that mean? So modify the form of parameters to allow efficient learning. So here is that the key idea here is that instead for us to to update the whole parameter the way it is, we do what we call reparameterization method. I don't know if anybody knows what we mean by reparameterization in mathematics. Can anybody help us if you have an idea? So can anybody? Anybody knows what we mean? No, no, no. Hey, um, so
Okay.
yes,
Yeah, it's like you are describing a different parameters with different objects.
describing
An
different
object with different parameters. Yes.
an object with different
Parameters.
parameters. Hmm. Anybody can try again. So I'll give you 2 minutes to tell me the answer. You can chat with your chat GPT. Ask chat GPT, what do we mean by this? Anyone can try? Anyone can try. Oh, nobody has hear about something called LoRa. Nobody here before. What is LoRa?
The only thing I know about LoRa is it means low rank adaptation.
Yes, yes. Because if you look at this one here, for example, here, you can see we have large matrix M, right? M by N. How many parameters does it have? 24 parameters, right? But this, we approximate it to something like this. And how many parameters this does have? 20 parameters, right? It has 20 parameters, right? So can anybody give us some guess? We can see here, for example, we have M by N and we now approximate it. You can see this is not equal. We are saying we approximate. We have something like this. And you can see here it has 24 parameters here. And now here it has 20 parameters when we approximate it. What is this telling us? This is telling us, for example, um, you know, training, uh, a model with huge, weight matrix, right? We can approximate it into some, product of two smaller ones. So if we approximate it, this is big, but if we approximate it to product of some smaller one, it's easy for us to do this one because it's small. It's easy for us to do this because of the multiplication. So this is the meaning of that. So this approach, actually, this is a commentary, because training full weight matters in large model is expensive, billions or millions of parameters. Instead, for that, we do what we call reparameterization. Maybe in mathematics, reparameterization, what do you call it? We have Sani, you are the professor in mathematics. Tell us reparameterization. Maybe you know more about us. So we use reparameterization that let us get similar result with the fewer parameters rather than the bigger parameter. So this is a key idea on what this approach is. So here, fine tuning to update to LLM in the low dimension space. Um, what this is telling us is that pre-trained model, we high dimensional parameters. For example, we have billions of parameters and something like that. Fine tuning, we know it's update low intensity dimension can be captured in fewer dimensional. So instead for us to update, do for this huge, metrics, the idea is, we can basically, do this and approximate it into these smaller ones and update these ones, which is easier. So this is a key idea. Even though a model has billion of parameters, the meaningful changes during fine-tuning can be represented in a much smaller space. So instead for us to do changes in the big, we can do in the middle. So this is basically one of the idea of how reparameterization is, and this is, the key idea of LoRa architecture. So we can see that the approaches we have seen, full fine tuning is baseline. Like full fine tuning is expensive, right? You train the whole parameters of the model, which is 100%. And you can see, for example, you may need at least 80 GPU, right? But what about adapters? We can see adapters, prefix tuning, prompt tuning, all these are additive methods. You add something to the structure and training parameters, for example, this is Z, and you can see the, GPU memory you may need may be small, right? We have bitp, all this one are selective method, for example, and you can see you need this. And then we have LoRa, QLoRa, DORA. They are based on what we call reparameterization. They are not adding anything. They are not selecting anything, but the reparameterization of your weight models, right? Instead for them to train a very huge weight of large, so the reparameterization to approximate it into smaller weight, something that we have seen here. Instead to do all the original weight matrix here, so we do low rank. This is a low rank because here we have 4x6 right now. Here you can see we have 4x2, 2x6, which is low rank stuff. So that's what it means by that. And here you can see these are some of the LoRa and QLoRa, some guide on how to do how many things it does. So this is basically fine tuning. We have seen in a nutshell that fine tuning is basically an approach where you take your model after training a base model, and you want to adapt the model to a particular domain. But it turns out that full fine tuning is very expensive. You cannot train models with 100% trainable parameters. And especially for us here in Africa, we don't have, a very GPU, number of GPUs. We can use some tricks that allow us to fine tune a bigger model. So these approaches are what we call parameter efficient fine tuning. And they have three approaches. One is additive, one is selective, one is parameterization. That's what we have seen. The next thing we are going to look at is instruction tuning. Can anybody volunteer to tell us what is instruction tuning in LLM today? This is some of the most, very good stuff that we have been seeing. Instruction tuning. Can somebody? Okay, so before that, let's look at this. You can see one major issue with LLMs is the mismatch between the training objective and user objectives. Training objective and user objective. What does this mean? You remember when we train LLM are basically trained to predict the next word, right? LLM are typically trained for next word prediction. But while users want the model to follow their instruction helpfully and safely, right? For example, let me show you this an example. Maybe I have an example. Oh, I don't have. Okay. Let's look at this one. Write a poem that describes a sun getting dipped in chocolate. Write a poem that can do that. And you can see here, it should be a haiku, and it should be about a sun getting, it should be a haiku, and you can see it repeating itself, like, there is no sense in what this is doing. This is llama based, not instruction tune. So now today, when you see LLMs, large language model, you will see some large language model, they are called instruction tune models, instruction tune. Meaning that they have been further trained using what we call instruction tuning data set. So this is Llama 8 billion base. You can see the first is the input prompt. So you give this one. So you can see the output here is not reasonable. Like, this is not kind of what we expect, a good model to give a poem. The reason most of their training data is not in instruction output format, instruction output format. So when you have your base model. You train it for the first time. That is the base model. It's not instruction tone. If you want your model to, when you write your model, write a poem that describes a son to give a deep chocolate. Using the base model that you just find to pre-train may give you some rubbish. This is not good. But if you want it to give you something really cool, like, really a good poem, then you need to take that language model from the base to teach it how to write a very good poem by further training it on a sample of poems, maybe like, 1,000 poems. Then you say, okay, maybe the example of poem, write a poem about, someone being a president, and you write a very beautiful poem. So you write a several poem to teach the model. Now, what you need to do is you need to take that data set, which we call instruction tuning data set, and now further fine tune your model with those samples. Now your model will now know, okay, if I'm using like, poem, this is the format. So if you ask the model, even another poem that is not within the instruction tuning data set, the model can be able to write a new poem excellently. Okay, so this is what I've seen. So that's why we say LLMs are typically trained for next word prediction on large corpora. That is the first training. We pre-train a language model with, But while user want to follow the instruction, you want to ask the language model, write a poem to me, for me. But you didn't treat that model to follow your instruction, like, to write a poem. Only you teach the model is to predict the next word. That is what we do in pre-train. Now, to solve this issue, we now have what we call supervised fine-tuning, or SCT is proposed serving as effective technique to enhance the capability and of large language model. So this is an example of instruction tuning. Look at this, an example. The first one, you need to give instruction and output. For example, look at this one, input to translation here. This is an example of input to translation tuning data. Translate this sentence to Spanish. Can you see instruction? Translate this sentence to Spanish. Top. Now look at the new office building was built in less than 3 months. Can you see the sentence? Now you can see the target. You something. Can you see the Spanish? So you can see the instructions. You put the tags and you put the output, right? Look at another, tax input, comma reasoning. Here is a goal. Get a cool sleep on summer days. Now look at the option. How could you accomplish this goal? You can see the option, keep stack of fellow and something, and then it keeps stack of fellow case improve, something like that. You can see that. So this is an example we call instruction tuning. So you need to create instruction tuning data set for several tasks. For example, you can see this is machine translation, common reasoning, sentiment analysis, conflict resolution. If you want your model to be good in 100 tasks, in NLP we have more than 100 tasks, then you need to create what we call instruction tuning dataset. Instruction tuning dataset, yeah? And that's how to do it. So for example, if you look at this one, we have your pre-trained language model, right? Pre-trained language model. And then you have your, instruction tuning dataset, instruction plus input. You can see I have instruction, I have input, and then plus output. You can see that instruction, input, and output. This is what we call instruction tuning dataset. You give it instruction, the data. You can see here we have instruction. Translate this sentence to Spanish. This is the instruction. Input, you can see the new office bill is the input. Output, the translation. So this is what we call instruction tuning data. And then you continue training your pre-trained language model, and now you have fine-tuned instruct model, right? That is what we call instruction tuning. Can somebody help us to Google your stuff and write to us any of the instruction tuning data set you see? Instruction tuning data set. Can you tell us an example of instruction tuning dataset? Google with your ChatGPT, instruction tuning dataset. Because there are several instruction tuning dataset out there. Can somebody tell us? Um, Have you seen any of the instruction tuning data set? Hey,
Yes, sir.
which one?
There is alpaca style.
Exactly. So there is another data set called,
52,000 examples. There is open assistant data set.
okay. Okay. Yeah. So a good example is alpaca data set, is instruction tuning data set.
Which
So try to look at the,
is for
okay, cool. So let's continue. That is what we call instruction tuning data set. Uh, you can see the key idea here is that a language model to execute tasks. The key idea by teaching or training a language model to execute tasks based on instruction, it will learn to follow and apply them effectively to new. Can you see that? To new previously unseen tasks. So even though I give it maybe task maybe 50, but when I give it a new task that is not unseen, it will be able to generalize from what it has seen. Yeah. That's instruction tuning. There I said. So you can see here what is the difference. One may say, okay, we have been seeing fine tuning, but now you are saying instruction tuning. So what is the difference between instruction tuning and the fine tuning we have seen before? Yeah. Somebody can add that. So what is the difference between instruction tuning and the fine tuning we have seen? So you can see basic fine tuning build a model that is good at performing a single task. Can you see that? When you want to see sentiment analysis, you create your data set for sentiment analysis and you fine tune your model. So that model can be good in doing sentiment analysis. But instruction tuning build a generalist model that is good at many tasks. So instruction tuning, you don't actually fine tune with one data set, but with multiple tasks data set, right? So you can see here, this is, pre-train and fine-tune. For example, you pre-train your language model, fine-tune it on one task. For example, sentiment analysis, and you can do sentiment analysis, right? But instruction tuning, you pre-train your language model, instruction tune on many tasks, A, B, C, D, E, up to the N, and then you can do that. You can see the difference between that, right? For example, of instruction tune language model, like Flan, can somebody tell us another example of instruction tune model? Instruction tune model. Just Google like the instruction tune LLM, something like, just search something like the instruction tune model, and tell me what is an example, one of the example instruction tune model. Just tell us one example of instruction tune model.
So yes, it's GPT-4 is fine instruction tool model, and also Plan T5.
Okay, yeah, good one. So yeah, of course, GPT is instruction tool model because they are excellent. They are from OpenAI. All these the LLMs that we see, ChatGPT, Cloud, all of them, they are instruction tool models, right? Because they can do multiple tasks, right? Everything they can do. But before they release them, they had to create instruction tool data set to continue to run this model on multiple tasks. For example, for sentiment analysis, they had to create instruction tune data set. For machine translations, they had to create instruction tune data set and continue to run their model on that. So now we have seen what is instruction tune. We have seen basic fine tuning. Now we have jumped into another thing, instruction tune. So this is an example. Pre-trained model or COCOBEL can't follow instruction in zero shot setting. Example, Llama with Llama 3, 8 billion base. The first sentence is the input, prompt, and look at this. So what is the benefit of SFT? Benefit of triple fine-tune an LLM on instruction to that bridge the gap between next word prediction and the user's objective following. Yeah, so you see that SFT, because pre-trained language model only know how to do prediction for the next word, but pre-train on SFT now make the model to become generalist, right? Yeah, so these are some of the benefit as well. So these are some of the how to construct instruction tune data set. For example, one of you can say, okay, I want to do some project. I want to create, create instruction tune model. Instruction tune model maybe for Llama, for Hausa. And then you need to create instruction tune data set first for Hausa. And now you continue training your Llama on Hausa data, instruction tune data, right? This is a good project. So, how does the instruction tune data set work? An instruction, which is a natural language text, you can specify the tag and optional input and output. So this is how the instruction tune data set will look like, which I already shown. You need to have your instruction like this. Translate this sentence to Spanish. This is the instruction. The input, the what you want, and the output. So this is basically the structure of instruction tune. These are some of the example of instruction tune data set. Flan, this is the data set, and you can see, a lot of instruction tune model. So you can see this is Llama 2 chart, ministerial instruct. So in fact, some model you can see they put instruct in them. For example, ministerial instruct, it means it is ministerial train on instruction tune. Llama 2 chart, you can see all of these, they are decoder only model, but here Plenty Pipes is encoder decoder as well. So this is Plant, it's a data set, you can see there. In fact, there is a work that, automatically creates self-instruct data set. It is possible to automatically generate instruction tuning data set. So you can automatically create instruction tuning data set. This work automatically create instruction tuning data set. Of course, you can say, okay, you can automatically create instruction tuning data set for Hausa, and you can, follow some approach to do that. It's a good work. Alpaca is basically, instruction tune data set as well, high quality instruction data set with self-instruct using OpenAI, text DaVinci O3. So this is a data set from Stanford. They create this Alpaca data set for instruction tuning. This is also another data set, Vicuna fine-tuned Llama model. But again, this is another problem. Do you think after we create instruction tuning model, we are done? Like, that is the end of the world. We have a perfect model. No, instruction tuning is not enough. So why is not enough? What to say, reduce carb intake. For example, what is the best way to lose weight quickly? Now, our instruction to model can say, okay, reduce carb intake, fiber, protein, increase vigorous exercise. Yeah, good one. Yeah. It tell us what we need to do to reduce, lose weight. But the insertion tool model cannot say this. You should stop eating entirely for a few days. We cannot protect or prevent the instruction tool model from saying this. Maybe you can tell that person, you should stop eating entirely for a few days. So if it tells this one, this is very, toxic. If somebody stop eating, will die, right? So instruction tune can do this, but it cannot prevent this. That means instruction tuning your model is not only it's not only enough. You need to also explore approaches to basically, make the. So that's where something called alignment. Alignment can prevent certain output that model assumed to be correct, but human consider wrong. So look at this idea. This is a new research area in AI and NLP called LLM alignment. So the model can output this, which is good, and the model can output this. But how can we prevent this? Right? How can we prevent this? How can we prevent the model from saying this? That is, we need to do what we call LLM alignment. We need to align the model to be safe, to be culturally good, and something like that. And if you, go to your ChatGPT, tell me, what is LLM alignment? What is LLM alignment? What is LLM alignment? LLM alignment. Anybody can tell us what is LLM alignment?
So LLM alignment, means making a large language model behave in a way that matches human values, intentions, and expectations.
Excellent. So that's what we call LLM alignment. Basically, is a way that we actually make LLM to follow, human preference, the value, and ever other something related to that. So we will come to alignment. This is something that we're gonna do as well. The alignment. Okay, so instruction tuning can make the model generate the right kind of answer, but it cannot reliably stop model from producing harmful, culturally inappropriate, misleading, or unsafe. Right? So instruction tune model can teach the model to follow itself, but alignment teaches it to follow human values and avoid harmful output. So this is a new thing that we haven't looked at. That is called alignment. It's basically teach the model how to avoid harmful output and follow human values, right? So that brings us what we call LLM alignment. LLM alignment. So this is a very good research area now. I have some current student working now in this. I have some student from AIMS Cameroon. Student from AIMS Cameroon. They are working on this LLM alignment project in their masters, and there's another PhD student. We are working on LLM alignment for health, mental health, and something like that. Also, I am gonna have 2 postdocs to be working on this LLM alignment this year. So this is very recent work. People are working. It's a good area if you want to do something related to that. So what LLM alignment? Alignment prevent output that human consider wrong, rare, because language model does not consider anything wrong. You need to tell it, even if the model internally believes they are plausible or correct. So even if the model think that this is a correct answer, but alignment prevent output that are not well aligned with the human. So there's several alignment method. We have reinforcement learning from human feedback, constitutional AI, safety policy, preference modeling. These technique target what the model is allowed to generate, not only how the model is sort to behave. So these are all approaches that allow a model to generate what is right based on human preference. What is the time now? Okay, we still have 15 minutes. Okay. All right. Okay. 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 So these are some of the approach you can see for alignment of LLM. Number one is the reinforcement learning from human feedback, safety policy for reference modeling. So what is the first one? Reinforcement learning from human feedback. So it is a way to train model to give answers that human actually like and find helpful. So you can see that it is just a way to train AI model to give answers that human actually like and find it helpful. So let's look at an example, the problem they solve. So for example, after we train a language model using a huge amount of data, the AI model knows grammar and facts, right? But it doesn't know how to be helpful, how to be polite, what kind of outside human prefers. So model doesn't know this. It does, however, it does know many things like the grammar and everything. Now, question: how do I bake cake without a RLHF? The model might say, somebody may say, how do I bake a cake? So without RLHF, cake, flour, oven, 2 shot this is unhelpful because he just say, how do I bake cake? He just say cake, okay, flour, oven. He just give but this is not helpful, right? It's unhelpful. We want the model to be helpful, right? Even the model return this is something related to how to bake cake. But what about here? The model here he gives here is a 50-page essay on the history of baking. Too long of topic. The model give this, which is also not helpful because this is not what also human prefer. Because how can you give me a 50-page essay on how to do a cake? But here we can see I don't care about your cake. You can see this is rude, it's not polite. So LLM can be all this, stuff like, is giving an answer, related answer, but that's not the answer what a human prefer, right? And they are not helpful, right? So how can we teach a model to be helpful, to give us a preferred human? So in that case, human must teach it, right? We human that we want the model to do something that we like. We must teach the model that this is what we like. We don't like this one. This is what we like. We don't like this one. This is what we like. We don't like this one. Yeah. So we need to train it in a way, right? We need to train it. That is where the RLHF comes, reinforcement learning. So RLHF, the model learn to say, to bake a cake with RLHF, preheat your oven, mix your flour, pour into pan, and bake for 30 minutes. So you can see this is helpful, clear, and appropriate. So if you do RLHF, that means it is going to give you this. So we can see from here that all these ChatGPT, they have now been, aligned because they give us some output that, is what we want, right? It gives us some output that is what we want. So how does that work? How do we teach a model using RLHF? Yeah, that's another thing. How can we teach a model using that? So, RLHF, what it does is it asks human to compare response rather than write them. Showing two responses, asking which prefer its model. So let me show you. So maybe this will be very scanty explanation, but I think it's good we can learn from this. So the idea is collect human preference data. So the first step before you do RLHF, before we do this one, RLHF, we must do instruction tune first. We must tune our model. That is the second. So the first thing you need to do is pre-train your language model, get an instruction tune data set to train your model, and then you do RLHF as the next layer. So let's look at it. So, the first thing is collect human demonstration data. Number one, supervised fine tuning, right? This is your base model. We know our base model, and you now continue training your model using supervised for the training data, and then you have SFT model. So you can see here, this is your preference data or super SFT data, which we already saw. Remember, we talk about SFT data right here. Yeah, all this one, instruction tuning data set, SFT. This kind of data set, right? Yeah. We collect this instruction tuning data set, right? So the first thing is LLM alignment is you need to SFT your data set, and now you have instruction tune model, right? Now, the next thing is, okay, we now have SFT model. It can follow user instruction. It can do sentiment. It can do translation excellently well, but it does not, know what is right, what is wrong. So what you need to do is, you now, you can see here, this is a prompt, right? This is a prompt. Let me do this. You can see this is a prompt, right? And now this is your SFT. You can see this is SFT using SFT data you train. Now you create a prompt, for example. Write me a step how to do a cake, baking a cake. And SFT model, because it's not further trained to know what is good or not, can give maybe multiple answer. You can see here we have answer 1, answer 2, right? So maybe we can give it to give us answer 4 up to 1, 2, 3, 4. And now here we now have to have a human. Can you see a human? A human now can select which answer is better. So a human can tell, oh, answer 1 is better because I asked this guy maybe to tell me the step to do, cook a cake, to create a cake. Now this guy give me answer 2 give me PPT page to create a cake, but answer 1 give me some a step like put water or something. So human, you and I human can now say, okay, oh, answer 1 is better than answer 2, right? So this is what we call human preference data. Human preference data set. Can you see that? Human preference data. Yeah, that's what we mean by this human preference data. Human preference data. Now, that is it. Now, we now have this, then we now can take our model. We can now we have this human, we collect human preference data. We now train what we call a reward model, right? Here you can see what we have supervised fine-tuning model. You can see that supervised fine-tuning model, and we take this supervised fine-tuning model, can you see that, and now create a data set, human preference data. So now here at the end of the day, we will have a data set where we know which one human prefer among multiple options. Given a prompt, these are multiple answers. Which one human prefer? So we have what we call human preference data. Now we now train a base LLM with the human preference data, and then we have now here reward model. If we train the model base LLM with human preference data set, that base model will know now the best answer one is the best answer. So it will always correspond to answer one. This is just an example. You may have multiple, like the human preference data can be 1 million data point, 100,000, where you give a prompt, it give multiple answers, and human like you need to sit down and annotate the data. This is what we call data annotation to select the option. Maybe you have 4 options, the answer is 1 to 4, and the human must select which one is the best good answer. And this data, now you select your base model and now continue it. You can see now you have reward model, right? Reward model. And now here we now have what we call PPO, which is basically algorithm. So here yes, we have Buhari Nasser. You want to ask a question?
Yes, sorry, sir. I just want to clarify. In this second step, this base LLM, are we training the base or are we building on the fine-tuned model that we built in the previous step?
Yeah, so that's a good question. What his question is that now we have here we have a base LLM, you can see that, and here we have a base LLM, right? And so here when we get our data set, data set supervised fine tuning, we get something called SFT, right? SFT for return language, and then we get this SFT to collect human preference data, right? Now, since we have this human preference data, right? We have human preference data, which one is better among this thing, and now we're gonna do supervised fine tuning because this is whole supervised, because we have a data with the data question and answers. They are supervised fine tuning. So now here we're gonna give our what we call train a reward model. That is a reward model, because a reward model is a model now that will know which answer is much better. So now his question is that, are we doing still training from base LLMs, or are we using SFT here? If we are using SFT, you can see we are building on top of previous steps. So I guess here we are using SFT because SFT training, continuous training on SFT data give us training on instruction tune, and then also we have reward model. So here I think I have another slide. In the next slide maybe it will show us we are using the instruction tune model. I will show us in the next slide. And now finally here is what we call is optimize policy. You can see that optimize policy. So here you can see what we said in the next: train a reward model to predict human preference. Use RL, reinforcement learning, and this is an algorithm PPO to make the LLM maximize the reward. So here you can see now we train a model. We have policy here. So what means here is that we have now algorithm called PPO. Now you can see here we have a prompt, right? We have a prompt, and now with this prompt, we're gonna ask a question to the model, right? We're gonna ask a question to the model, and now when this model give a question, an answer that is not right, because we already trained it to give us an answer that is more or less all right. But when we give it a prompt and give us an answer that is not right, we're going to update the policy, because reinforcement learning is a way where we have an algorithm where it maximizes the or reward something that is correct. Because if it gives us a wrong answer, then we update it. There is some policy update, it will penalize it, for example, now we have a robot, and the robot now is working, and when he hit when the model hit the wall, maybe the policy will update the policy that because he followed a wrong way, and now the robot can update its parameter to follow a correct way. So this is a policy stuff, and it will continue this optimization, this stuff. Dr. Sani, maybe you can help us also add more, because this is your stuff like optimization. Can you add anything here, Sani?
Hello, doctor. Sorry,
Mana.
I was not like I was carried away. I was doing something at the same time. But can you mention it again?
No, it's all right. It's okay. Just continue. I just want to talk to you. So we are talking about something optimization here, but I know
Okay.
you did optimization, but it's all right. So yeah, so that's basically what we talking about at LHF, reinforcement learning, where we need to use collect preference data, train a reward model, and now use an algorithm. So there are different kind of algorithm to optimization. We have PPO, we have DPO, and many other stuff. So let's look at this. So this is ChatGPT approach as well. You can see that collect demonstration data and train the proprietary model, a prompt, okay, blah, blah. So this is a ranked model. This data is used to train a reward model, right? A reward model, optimize the promise against reward model user reinforcement learning. A new prompt example, okay, PPO. Yeah, so basically, as I said, this one is SFT model. It should be SFT model, I guess. Yeah, and this is basically how ChatGPT and cloud and everything is trained now. You collect preference data, you train a reward model, and now you use optimization algorithm to do this. So that's basically how these things have been done. We try to I will give a reference, that we can read and learn more about this stuff, because we may not discuss a lot how it's supposed to be. Okay. Any question again? Any question? Okay. So let's continue. Okay. So this is basically, you can see that the steps we have seen, the first one is SFT model. Start with an instruction-tuned SFT model, right? Now collect human demonstration, annotated thread idea ransom, train best supervised by tuning, best for preference collection. Then you have step 2, reward model. For each prompt sample key response, human train a model separated with scale ahead to predict the preference score. This is a reward model. Right, and then you do your PPO fine tuning. That is that. Okay, and then the next thing is we do have the alignment algorithms. So we have several kind of alignment method, or we have several kind of alignment algorithm. Some of them you can see them here. We have what we call DPO. We have what we call GRPO. We have we have a lot of these algorithms that can be used to do to do alignment. That we'll use alignment, use for alignment. So now we have seen the alignment RLHF that it can be used to do using reward model, right? Reward model. But one question they're talking about is that using reward model here, using reinforcement learning is a bit. What is the time now? Oh, it's already time. Okay. Yeah, so that makes sense. It's already 3 o'clock. So I think we can continue with the second part of alignment, this section, these alignment algorithms. We can continue with them next week. Yeah. Okay. I think we can continue next week with this. All right. Thank you very much for everyone for joining. We can continue next week with this. Any question?
Okay. Thank you so much, Doctor. Thank you. Thank you. Really appreciate. I just want to ask one last question.
Yes, 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 yes.
Sorry, please. This is my first time joining this. I'm currently studying my master's. I'm now in Porto, Portugal.
Oh,
Uh,
Porto.
yeah,
Which
exactly.
university?
Sorry.
Which university?
Oh yeah, so it's called Lusafona.
Oh, okay, Lusofona.
Yes, yes, exactly.
Ah.
So I'm an Erasmus student, like I'm studying artificial intelligence for sustainable societies. We started in Estonia and now I'm in Porto. Next semester I will be in Finland. So I find this
Oh, ga
yeah.
Sani na ai sai ga Sani na ya kamata ka haɗu da Sani yana nan Sani na ne garin kuma Finland ne ko?
Poland ne. Erasmus kake yi ne, Buhari?
Erasmus ne,
Oh,
sir.
Sani ma Erasmus kai Erasmus kai ma Sani ko?
So yeah, we can keep in touch. Za mu iya yin magana daga baya. But you
Maybe
can go
ma
ahead with your question.
da akwai Sadiq shekara ta wajen 6 a Porto ne ma kam. Da akwai Sadiq abokina Sadiq yanzu yana nan tare muke yana nan Porto shi ma. A wajen Lusana a wani waje kake a nan wajen university kake zaune ko a ina ne da nisa inda kake?
Banda nisa ina gaye ne.
Oh, kana Gaya.
Okay, okay.
Baka kusa da makarantar da yake nan.
Gaskiya ina tafi wajen 15-20 minutes in je makaranta.
Ka san masallaci?
Ina zuwa nan Masjid Hamza na wani Bangladesh.
Na gane, na ga. Halal shopper.
Shi ma akwai wani kusa da nan masallacin shi nake zuwa abinci.
Okay, so abinda za a yi zan yi dropping din MTN lamba ta here in the chat. Chat to me zan haɗa ka da Sadiq yana nan so sai kai magana da su da nan 6472 okay.
Thank you so much.
Yawa, ina jin
I
ka.
just if I can get the previous recording because this is my first time playing. Or is there
Okay, we
any
have
way?
the recordings. We have the recordings in the YouTube, I think. Yeah, we have the recordings in the YouTube.
Okay, so what's the name
Yeah,
of the channel?
yeah, we have Abdul Jalil, if you can share our group chat, whether House NLP group, so he can join us. You can join, and you can look at the our the link you can use to join.
Okay, thank you so much.
Na je ma number na as well, Buhari.
Okay, na ga dai okay yawa na ga na gode zan na dauka. Insha Allah I will connect.
Okay. All right, cool. So yeah, thank you very much, and do reach out if you have any question. Thank you. Bye bye.
Thank you.